Fresh water. Life cannot exist without it. It's not only the water we drink, it is a vital part of our daily existence. Yet this critical resource is increasingly becoming scarce. Nearly half of the global population is facing severe water shortages. Droughts are occurring frequently, affecting countless regions around the world, and not just the developing world. These alarming trends are also placing crop production and food production at risk, disrupting the lives of many communities, while water sources are persistently drying up. These issues are no longer limited to the Middle East and Africa. Water shortages affect several regions in the US, Caribbean islands, Southern Europe, Middle East, Africa, as well as Asia and many other coastal geographies. Considering the unlimited availability of seawater, it is not surprising that desalination was embraced globally as a logical complement to rivers and aquifers, which are increasingly disappearing around the world. In fact, seawater desalination has become the go-to freshwater supply alternative throughout the world and is expanding at a considerable rate. Over 20,000 desalination plants are currently operating around the world. These are essentially two desalination methods: thermal desalination and reverse osmosis. Thermal is the oldest form of desalination. As the name implies, heat is applied to the seawater to make it boil. The released steam is cooled, changing its state to liquid. But in the 1960s, reverse osmosis technology was developed and is now a de facto desalination industry standard. The major difference between the two methods is that reverse osmosis doesn't use heat and doesn't boil anything. Instead, the process applies tremendous pressure to force the seawater through a fine membrane to separate the saline and water molecules. Certainly more efficient than the thermal desalination method, but not without significant environmental and productivity implications. Just to name a few, firstly, continuous dumping of a highly concentrated saline solution back into the sea is destructive. Secondly, lots of energy is expended to maintain as much as 200 psi of pressure needed to force seawater through superfine membranes. And thirdly, maintenance, replacement, and disposal of membranes is costly and more intensive and disruptive. Let's explore these concerns in some further detail. A key characteristic of reverse osmosis is that half of the seawater that is ingested for desalination is returned back into the ocean with twice as much concentration of salt. Releasing huge amounts of hypersalty water or brine back into the ocean is dangerous because the impact on the marine life may be irreversible. Right now, the industry is producing over 37 billion gallons of brine per day. Nearly all of it is emptied back into the ocean. And because brine has a much higher salt concentration than regular seawater, it can wreak havoc on the plants and the marine life, which cannot be sustained. Moving on to the issue of membranes, reverse osmosis membrane is a complex multi-layered construct. Microscopic holes keep salt molecules from passing through to the freshwater chamber. Eventually, the accumulated salt particles render the membranes unusable, which warrants their frequent replacement, shell preparation, cleaning, and related maintenance activities. The frequency of membrane maintenance, replacement, and disposal are costly and labor-intensive. Finally, the energy required to operate reverse osmosis plants is significant, and considering the deployment scale of the reverse osmosis plants worldwide, this is both costly and environmentally unsound. Clearly, current desalination technologies are in many ways suboptimal, which allows us to introduce a new breakthrough desalination technology. The principle of the AQUATIQ desalination technology is cold boiling. That is, water can boil at room temperature if certain conditions are met. In this example, a container of water at 23 degrees Celsius will be placed inside a chamber connected to a vacuum pump. Once the water container is enclosed and the vacuum pump is engaged, it lowers the pressure inside the chamber to the point where the water starts to boil, while the temperature remains effectively unchanged. Using this principle, we proceeded to design the vacuum chamber that would be used at commercial production scale to cold boil seawater so that the steam collected during the boiling cycle would be condensed into fresh water. We selected a stainless steel fabrication specialist who built the chamber to our custom design specifications. All materials and components used in the construction of our vacuum chamber were made entirely from marine steel. That is 316L grade stainless steel, which can effectively resist seawater corrosion. The chamber was rigorously tested for vacuum sustainability before being shipped for further design. The dimensions of the chamber allowed an optimal fit with a standard shipping container. The container serves multiple purposes, including ease of shipment, chamber surface protection, and the ability to stack chambers vertically to allow scalability as production volume demands grow. The next step was to manufacture the equipment, which we have custom designed for our desalination process. Equipment included seawater preheating system, condensate chiller, thermal compensators, as well as standard components such as liquid ring vacuum pump, seawater transfer pump, and so forth. The final step before proceeding to the pilot site was to install various thermodynamic components inside the vacuum chamber. We chose to conduct the test pilot in the Cebu province of the Philippines, specifically Mactan, Newtown Beach. The long pier and easy access to the deep ocean stream made Mactan, Newtown Beach an optimal pilot location. So, after preparing the platform, making electrical connections, laying the intake pipeline, and configuring the equipment, we proceeded with the test. The first step was to preheat the incoming seawater. Our process requires the seawater to enter the chamber at around 42 degrees Celsius. The preheating occurs as the water passes through the thermal oil-based heating system. Heating step, we also use thermal compensators to maintain temperature consistency inside the evaporator section of the chamber. A series of heat exchangers and other auxiliary equipment ensure constant water temperature and flow rate. Once the water enters the chamber, we engage the liquid ring vacuum pump to lower the pressure inside the vacuum chamber. The seawater enters the evaporator section of the vacuum chamber at around 42 degrees Celsius, which is our target. The pressure gauge indicates the depth of the vacuum level inside the chamber. At around 350 torr of vacuum pressure, which is just below half of the atmosphere, the gases begin to separate from the seawater in the chamber. Removal of various dissolved gases and other contaminants from the water, including carbon dioxide, purifies the seawater considerably and raises the pH level of the resultant drinking water. As the vacuum level reaches 65 torr, you can begin to see the start of the boiling process. As the pressure drops further, down to 60 torr in this case, the boiling intensifies further. Now at 55 torr and below, the target boiling point is reached. At this stage, the condensation equipment kicks into gear, which allows the freshwater production to begin. Because the condenser equipment is uniformly distributed throughout the condensation section of the chamber, the freshwater production is evenly distributed. Once we were satisfied that the process works as designed, we placed several containers inside the condenser section of the chamber to collect the product water for laboratory testing. One of the advantages of the AQUATIQ desalination process is that the water is immediately suitable for human consumption without the need for further post-processing. As the lab report confirms, the quality of the AQUATIQ water features superior performance indicators in terms of pH, total dissolved solids, and hardness levels. Specifically, based on the lab analysis report, pH level is 7.44, TDS below 16, and total hardness under 13.